A college sports league has found that 5% of its players use an anabolic steroid. The sports league would like to contract with a testing firm. One firm claims that their tests correctly identify 95% of users, and that non-users only test positive 6% of the time. To evaluate the efficacy of their tests, you want to know what's the probability that someone who tested positive is actually a user. Let's collect some of the things we know. 5% of its players use an anabolic steroid, so the probability of being an anabolic steroid is 0.05. Knowing that the test correctly identifies users 95% of the time tells us that the probability of testing positive, given that you are a user, is 0.95. Lastly, knowing that non-users only test positive 6% of the time tells us that the probability of a non-user testing positive is 0.06. Our question is to ask, what's the probability that someone who tested positive is a user of anabolic steroids? By the definition of conditional probability, we have a formula for what A given T is. It's the probability of A and T happening divided by the probability of T. Here, these are numbers that we don't know. By mapping out different outcome possibilities, we can calculate what our missing information is. Our given information tells us the probability of A, the probability of T given A, and the probability of T given A complement. This is enough to find that the probability of A and T equals 0.05 times 0.95. We can find that the probability of A complement is 1 minus 0.05, which is 0.95, and that the probability of A complement and T is 0.95 times 0.6. So we at least know the numerator of our problem. But we still don't know the probability of T. Here there are only two paths that lead to T occurring. This tells us that the probability of T can be equivalently expressed as the sum of the probability of A and T plus the probability of A complement and T. In this case, it means that the probability of T is 0.05 times 0.95 plus 0.95 times 0.06. So we get that the probability of A given T is 0.45 repeating. In the context of this problem, this result means that less than half the people that test positive are actually users, which means this might be a very bad diagnostic. The process we just went through is encapsulated in Bayes' theorem, which can be stated as the probability of B given A is the probability of B times the probability of A given B divided by the probability of B times the probability of A given B plus the probability of B complement times the probability of A given B complement. As another example, let's suppose we are told that the probability of some event L is 0.005, that the probability of some T complement given L is 0.01, and that the probability of T given L complement is 0.2. Our question might be to find the probability of L given T. By Bayes' theorem, the probability of L given T is the probability of L times the probability of T given L divided by the probability of L times the probability of T given L plus the probability of L complement times the probability of T given L complement. We currently know what P of L is, and we know what the probability of T given L complement. We still need to know the probability of L complement and the probability of T given L. To find the probability of L complement, we'll use the fact that the probability of L plus the probability of L complement is 1. So 0.005 plus L complement is equal to 1, meaning that the probability of L complement is 0.995. To find the probability of T given L, we'll recall that the probability of T given L plus the probability of T not given L equals 1. This means that the probability of T given L plus 0.01 equals 1, and that the probability of T given L is therefore 0.99. So we get that the probability of L given T is the probability of L, which is 0.005, times the probability of T given L, which is 0.99, all divided by 0.005 times 0.99 plus 0.995 times 0.2, and that this is approximately 0.024.